In this video, we will talk about shear forces and shear stresses. What are shear forces? Shear forces are forces acting in the plane. If you call this force V and divide it by the area, you can find an average shear stress. But in reality, this distribution is not uniform. In reality, on the surfaces, on the top and bottom surface, the shear stresses are zero. The maximum shear stress is on the neutral axis of the section. So how do you determine the shear stresses for a given point in a section? Let's take the point P, and the shear force V is acting. The formula we're going to use is this formula. We will not derive it, but only show how to use it. Well, shear force has to be given. I is the moment of inertia for the neutral axis of the section. I is when you draw a line through point P parallel to the neutral axis. T is the width where the stress has to be calculated, namely in point P. Then we have a new value, which is Q. How is Q defined? Q is defined Y prime times A prime. A prime, this area above the line is the area A prime. You have to calculate it. Then you have to find the C prime, which is the centroid of this area. And Y by prime is the distance of this centroid from the neutral axis, the distance between this centroid. So if you know these, you can calculate Q and find the shear stresses. Okay, let's do this calculation for a rectangular section. The height is H, the width is B, and I like to know the shear stress in point P. I draw a line parallel to the neutral axis and determine this area. Well, this I need to determine the Q value. It is Y prime times A prime. What is Y prime? Y prime is the distance of the centroid of the dark area from the centroid of the whole section. That is this value. For this, I have to determine this distance. Well, how do you determine it? So you can determine this value as H over 2 minus Y, and that is half of it, H over 2 minus Y divided by 2. So now you have almost everything. So this is which distance? That one. That is Y plus H over 2 minus Y divided by 2. And then A prime is B times, well, this. That is H over 2 minus Y. Okay, this is your Q value, which you need for this formula. I is 1 over 12 BH cubed, and T equals to B. Now you have these values and you have V. Put everything into this formula, and what you find is this mathematical expression. So it is a parabolic distribution. Let's put some values. If you put instead of y h over 2 or minus h over 2, you will get for both cases 0. These are these 2 points. If you put y equals 0, then you find that tau equals to 6vbh cubed times h over 2 for minus 0. So this one goes with that, and at the end you will have 6 over 4, that is 1.5, v over b times h. We know BH is the area of the whole section, and we have discussed that if you take the shear force and divide it by the area, you find the average shear stress. So the result is, for a rectangular section, the maximum tau value is in the middle here, tau max, and it is 1.5 times the tau average, which you can find by taking the shear force and dividing it by the area. So you see here this written as a clear result. Average shear stress times 1.5 is the maximum shear stress for a rectangular section. In summary, shear stress distribution parabolic, upper and lower surfaces 0, maximum stress is in the middle, but for rectangular section this can be calculated 1.5 times the average shear stress. Well, if you look at other sections where wide flange beam, this one for example, you see the stress distribution is also similar, but you see here this flange, is actually where the shear stresses are acting. On the upper and lower surfaces, the shear stresses are very small. Why? Because the thickness in the upper and lower parts are higher than in the middle. But we know on the upper and lower parts, we know that the bending stresses are high. In the middle, the shear stresses are high. Okay, when we talk about bending in straight beams, for example, let's take two boards and you apply a bending moment. So when these boards are not glued together, we see that on the surface, you see there are some shear displacements. It shows that on the surface we have a tau, a shear stress. We can say the transverse shear stresses, like stresses in a section, they are always associated with the longitudinal shear stress acting along the longitudinal planes of the beam. You can see this, well, when you have a wooden beam. So when you apply again bending or shear due to P, and you see that the stresses acting along the longitudinal plane will cause some splitting. This is an interesting example. An example, rectangular cross section, B is 100, H is 125. shear force 3 kilonewton. Question, point P, for point P find the shear stress. And what is the maximum shear stress on the beam? We know that the maximum shear stress is on the neutral axis, and since this is 125, well, this distance is 62.5, and our point P is only 50 millimeters away from the upper surface, so it's not on the neutral axis. Well, let's start with the moment of inertia, BH cubed. That's the moment of inertia of the section. So let's take our point P, draw a line, and this is my area above this line, A prime, and the centroid of this area is C prime. I have to determine this distance. So I know that this is 50 over 2, that's 25 millimeters, and I know that this distance is, as you see over here, half of 125 minus 50, which gives you 12.5. So I can easily write that Q is first the distance, that is 25 plus 12.5, and the area, first the width times the height, 50, and so I do the calculation and find that the Q value for this point P is 1875 10 to the 4 millimeter cube. Okay, now I have my Q. You know the formula is V times Q I times T. T, the thickness is 100. V is given as 3 kilonewtons. Q we have determined, the I value we have also determined. Let's put the values together, and the calculation gives me the shear stress in point P, and your result will be 0.346 megapascals. Next question was the maximum shear stress. Well, we all know that's in the neutral axis. So this time my area A prime is this area. So it's 100 times 62.5. And the distance from the neutral axis Y prime is 62.5 divided by 2. And this is my Q value. The other values we already know. Put everything together, and the maximum shear stress on the neutral axis is 0.360 megapascals. So we remember we have derived a formula which says for rectangular cross sections the maximum shear stress is 1.5 times the average shear stress. Well, why not use this formula? Force divided by the area times 1.5. Well, the result is the same. So for rectangular sections, to find the maximum shear stress, well, easier solutions can be done, and this formula will be very useful. Another problem. A beam is made by gluing of two boards. You see this board. And let's take the blue color and the blue board. They have the same dimensions, 30 times 150, 30 times 150. So one board, the same board, and they have glued over here and made a T section. So calculate the maximum shear stress in the glue. Okay, this glue must be strong enough. So when there is a shear stress, yes, there will be a shear stress in this section. Well, the glue must be strong enough to withstand this maximum shear stress, and the problem wants us to calculate this value. First, we find this is my beam. Acting force is a distributed load. Instead, I put this frictional force and calculate the support reactions. So this is the V diagram of the beam. We see that on this corner in point B, this point, in this point, the shear force is 6.5. In C, the shear force is 19.5. Okay, the point C is the critical point. Why? Because the shear force over there is the maximum. So we have to calculate the shear force for this point and the shear stress for this point. Okay, this is my section. Well, this section will have a centroid and a neutral axis going through the centroid. We have to determine the position of the centroid Y bar. We will not go into details of how to determine the centroid. You will find videos in this playlist about this. So the Y bar is determined as 120 millimeters, 0.12 meters, and the moment of inertia going through this point is 27 10 to the minus 6 meter to the 4th power. Okay, let's calculate the Q value for point D. Well, for this, I need these two values. Well, if you draw the same section, the centroid of, this is my point in D, and my neutral axis is over here, and its distance from the lower end is 120. So what I need to know is the distance of the centroid of this area from the neutral axis. So you can determine it by taking this value, that's altogether 180, minus this value, that is 15, minus 15, and minus this value, that's minus 120. So this is what this is, the distance of the centroid from the neutral axis. And the area is not a problem, 30 times 150, then you have your Q value. Next, now we have everything. We have Q, we have the I value, the thickness is 30 millimeters. Let's put everything together using correct units. You find that 4.88 is the shear stress on the glued surface. It's on the surface and also on the surface. This end is the critical point where the shear force is maximum and the shear stress can be determined as 4.88. Your glue must be strong enough to withstand this stress value. Okay, in this video we have discussed the shear forces and the shear stress distributions in a cross sections, and now we know that the stress distribution due to the shear forces in a section is not uniform. So we shouldn't use the average tau value by taking the force divided by the area. Instead, we know that in a section the maximum shear force will be higher than the average, and it will be on the neutral axis. Thank you for listening.